We're talking about seismic data processing. We have seen in the first module, which is seismic acquisition, that data has to be first acquired, both refraction and reflection seismic data. Refraction seismic data precedes the reflection seismic data. Data is acquired with the objective to have a good signal to noise ratio. Signal to noise ratio is proportional to the square root of foldage. Foldage is the number of times the subsurface point is illuminated. Now, the objective after data acquisition is to clean the data more to have a data continuity as far as acoustic impedance is considered, and also to see that this data is meaningfully interpreted for structural and stratigraphic traps. Now, Earth, we know, are amalgamation of various layered. This layering are based on lithology by the geologist. For a geophysicist or an explorationist, it is actually understood in terms of density and velocity. Here we have the first layer where the thickness is h1 and the p wave velocity is vp1, the s wave velocity vs1 and rho1. Similarly, we have the second layer velocities and the density. We know the reflectivity is defined as v2 rho2 minus v1 rho1 by v2 rho2 plus v2 rho1. So we repeat it once again, v2 rho2 minus v1 rho1 divided by v2 rho2 plus v1 rho1. This gives the reflectivity, and I can repeat that reflectivity is positive, means there is a peaking. Reflectivity is a negative, that means there is a trough. In between we have the zero crossing. Now we can see here the energy goes inside the earth after the ignition, and it is captured by the geophones, which is given in the symbol of green. Now there are waves which don't penetrate the earth, which are lost, called air wave. We have refraction, as has been shown in the figure. We have direct wave where the energy is traveling directly from the geophone, directly from the source to the geophone, and then we have the reflection. In the reflection, we measured the two-way time. One way is the time required for the energy to travel from the source to the reflecting boundary and then come back to the geophone. All these data were acquired in SECD format, which is the time sequential data. The main objective of data processing is to convert it into trace sequential data. We also need to understand noise. Seismic noise can be either random or coherent. Coherent noise are ground roll, backscattered, multiple, sinusoidal, predictable. Methods of reduction: multi-channel filtration in TX domain, FK, which is the frequency domain, radon domain transformation, model-based noise elimination, and then there are random noise, non-sinusoidal, unpredictable. Method of reduction is CMP stacking. Also, we do predictive deconvolution in the FX domain. Before we go into the flowchart of seismic data processing, which is the basic flowchart we'll talk about today, there are many modifications on the flowchart to actually remove the artifact in the data, which is the advanced processing, and anybody who is interested to understand advanced processing can consult Otto Ilma's book on seismic data processing. We also need to understand what are primaries and what are multiples. Seismic energy that are reflected only once are known as primaries. Seismic energy that has reflected more than once are known as multiples. While virtually all seismic energy involves some multiples, the important distinction is between long path and short path multiples. A long path multiplex arrives as a distinct event, whereas short path multiple arrives so soon after the primary that it merely adds tail to the primary. Short multiples may obscure stratigraphic details even where structural aspects are not affected significantly. The attitude of long path multiple does not represent the portion of the section associated with their arrival time. Usually long path multiple have traveled more in the seismic, which is shallower part of the seismic section, than primaries with the same arrival time, so that they ordinarily show more normal move out and can be attenuated by common midpoint stacking. Here we see couple of example of multiples like ghost, simple multiple, peg leg, and also interbed multiple. Seismic data processing is a set of logical operations on the input data aimed at reducing the unwanted components, which is noise, gathering the wanted components, which is signal, generating a geological meaningful subsurface structure is the final objective of seismic data processing. What is a good signal? Elements of good signal is what makes the signal have three vital requirements: good signal to noise ratio, high resolving power, and adequate spatial coverage of the target. This is the basic flowchart of processing. We have the input raw data, which is the seismic data. We add field geometries and acquisition parameters. Then we edit the data. Editing requires, because all part of the data is not good, we may require to remove some part of the data where we apply muting. Then we apply gain. We understand that the amplitude has decayed in the deeper horizon because the energy exponentially decays. So we have to have an inverse filter called the automatic gain control, which is a window based amplitude enhancement filter to improve the amplitude of the deeper targets. As energy moves from the source to the farthest offset, the energy gets decayed. We also need to apply filter because all the data may not be useful to us. So we have a low cut filter, a high cut filter, and a band pass filter. Visualization of the groups of CMP can be in the common offset, common receiver, or short gathers. We have talked about the low velocity zone or the weathering zone, which has been removed in seismic data acquisition. If we have some component left, it is called the static, and we need to remove the static in the processing step. Velocity analysis is very important because velocity helps in doing NMO and NMO correction, and also converting the time data into depth data, which we have talked about in detail in a separate presentation. It is followed by NMO correction and DMO correction. If there is a dip in the data, we once again apply residual static, and we have the common midpoint brute stack. We filter the data once again. The amount of data which is useful for meaningful interpretation is acquired from the process data. We migrate the data and we stack it once again. We apply gain, and the final stack is made for interpretation. There can be variation in this processing flowchart. However, this is a basic flowchart followed by everybody in the industry. The first step is to convert the data from the seg-D to seg-Y. Multiplex to demultiplex, conversion of multiplex data to demultiplex data. Time sequential data is converted into trace sequential data. In a multiplex data, sample 1 from every channel is recorded, followed by sample 2 from each channel, and so on. The demultiplex rearranges the configuration to have all the sample of channel 1 in sequence from time 0 to end of the record, and then all the samples from channel 2, and so on. The signal consists of amplitude values spaced at a certain sample interval, usually 4 milliseconds, to obtain a certain resolution. In a high resolution work, a shorter sample period, 1 to 2 milliseconds, is often used so that higher frequencies can be recorded without aliasing. Then the step which is required to be applied is called muting. Bad data is removed from the trace sequential data. 3 types of muting is done, namely head muting, surgical muting, and tail muting. If the upper part of the record need to be removed, it is known as head muting. If some part of the record between 2 time periods, so one window between 2 times, then it is known as surgical muting. If the end part of the record has to be removed, it is known as tail muting. Automatic gain control is a rolling window operation. AGC is a process in which the gain in each channel is controlled automatically and independently from other channel. AGC type gain functions are applied to seismic data to bring up weak signals. Gain must be used with care since it can be destroy the signal character, which is not the objective. Program gain control can be used to preserve the relative true amplitude relationship. We should understand convolution once again, because convolution is a process which was utilized to convert the reflectivity into a seismic trace. Reflectivity at the interfaces of different rock layers were convolved with a wavelet which is the explosive source and which gave us the seismic traces. Now we added noise to it and we get the seismic traces. So if you have a signal, it is the input wavelet convolved with the Earth's reflectivity plus noise which represent the seismic trace. Now we would like to bring the reflectivity back. We need to remove the wavelet, and that is the objective of deconvolution. But before that, we once again talk about convolution. We have the seismic impedance log which is converted into a stichogram. The reflectivity functions is convolved with the input wavelet or pulse which gives us a seismic trace. Converting rock to reflectivity. All geologists will talk about lithology with depth. Geophysicists or explorationists convert it into impedance, and this impedance is converted into a stichogram where we have positive reflection as peak, negative reflection as trough, and in between we have the zero crossing. Deconvolution is a process which is applied to the data in order to remove the wavelet. Deconvolution compresses the basic wavelet in the recorded seismogram, attenuates reverberations and short period multiples, thus increases temporal resolution and yields a representation of the subsurface reflectivity. The process normally applied before stack. However, it is also common to apply deconvolution to stack data. Deconvolution has produced seismic sections with much higher temporal resolution. Deconvolution sometimes does more than just wavelet compression. It can remove significant part of the multiple energy from the section. To understand deconvolution, first we need to examine constituent elements of a recorded seismic trace. The convolution model. The Earth is composed, as I have told, of layers of rock with different lithology and physical properties. Seismically, rock layers are defined by the densities and velocities with which seismic waves propagate through them. The product of density and velocity is known as seismic impedance. The impedance contrast between adjacent rock layers causes the reflection that are recorded along a surface profile. The recorded seismogram can be modeled as a convolution of Earth's impulse response with the seismic wavelet. The wavelet has many components including source signature, recording filter, surface reflection and receiver array response. The Earth's impulse response is what would be recorded if the wavelet were just a spike. That's the objective of deconvolution. The impulse response comprises primary reflection reflectivity series and all possible multiples. Ideally, deconvolution should compress the wavelet components and element multiples, leaving only Earth's reflectivity in the seismic trace. Wavelet compression can be done using an inverse filter as a deconvolution operator. An inverse filter, when convolved with seismic wavelet, converts it into a spike. When applied to a seismogram, the inverse filter yields the Earth's impulse response. An accurate inverse filter is achieved using least square method. The fundamental assumption underlying the deconvolution process is that a minimum phase data is required. The issue is dealt with also in inverse filtering. The next step is stacking. Stacking is the process of summing all the traces with different offsets of single CMP, that is common midpoint, improves signal to noise ratio by cancelling random noise and boosting coherent signal, converts a large number of pre-stacked traces with different offset to zero offset section, shrink data size. And less computer time and cost, being averaging of sorts causes loss of resolution. Before I go into the migration, I will talk about normal move out. We have seen the distance between the short to the nearest geophone is the near offset. Distance from the short to the far geophone is known as the far offset. The reflection equation is given as t square is equal to t0 square plus x square by v square, which is called the normal move out. If we remove the offset, then we will have a zero offset data. However, there is a move out because of the data has offset. Now, normal move out correction is applied based on the formula which I have talked about. If we have a dip, then it will be represented as t square is equal to t0 square plus x square by v square cos square theta. You can expand this as t square plus x square by v square minus x square by v square sin square theta. T 0 square plus x square by v square is the normal move out, and then we have to apply a correction in the dipping bed called the x square by v square sin square theta, which need to be subtracted out, and this is what is known as the deep move out. Migration is also an important phenomena in the processing step, and there are various type of migration which are done to the data. Seismic migration is a set of technique for transforming recorded seismic reflection data into image of reflecting boundaries in the Earth's interior. In simplest form, in the Earth's interior, we have to correct certain distortion present in recorded wave field. The distortion can be caused by diffraction inside the Earth, which scattered the incident energy to range of receiver location, geometric effects caused by diffing reflectors, and velocity effects, which cause the seismic waves to change direction as they propagate from source to reflector to receiver. Migration is used to eliminate and estimate seismic velocity and to provide amplitude for rock property analysis. The migration heuristic assumes the subsurface reflectors are made up of point diffractors. The response of reflector to input seismic energy is the sum of responses to all the diffractors, and migration transforms the response to the actual reflector shape. Migration can be applied before the stacking, which is called the pre-stack migration. Also, they are applied after stacking, which is called the post-stack migration. To do migration, to apply stacking, and to understand also how to convert time into depth, we require understanding of velocity. Velocity tomograms need to be prepared. The most important velocity which we study is called the RMS velocity. RMS velocity is given as square root of v1 square t1 plus v2 square t2 plus v3 square t3 divided by t1 plus t2 plus t3 square root in case of three-layer dipping bed. In three-layer beds which are horizontal to each other, and stacking velocity is equal to RMS velocity if the beds are undipping or non-dipping. If the beds are dipping, then stacking velocity is equal to Vrms into cos theta, where theta is the deep of the bed. In a land seismic record, we can have various type of noise like facility noise, which we have seen here, reverberation, ground roll, air blast, harmonic noise, and Wakel noise. All these noise need to be removed from the data in order to have a meaningful interpretation. Once we have the data in hand, we should do an interpretation in the field itself. We prepare the base map, which was part of seismic data processing, because that was utilized to understand which shots has been shot in the previous day, which shot we have accepted, and which are the shots to be repeated. Once all the shots are blasted and all the recording are done and stacking is applied in the field to create the brute stack, we have 2D data and 3D data, which are inlines or crossline. We can see the geophone on the top of a 2D section or the shot points. We understand the shot point distance and the geophone distance. In the y-axis, we have the two-way time, and we can see lots of acoustic impedance which are running, and we need to interpret the zone of interest. We can do a manual interpretation or a interpretation with the help of computer to understand how to track a horizon of interest. Once it is tracked in the strike line, we will use one of the seed to go to the deep line. In this process, we will interpret both the strike line and the deep line. After that, we'll apply the loop time method, because while we interpreted the data, we have found many faults and there can be cycle skip and cycle splitting. So, loop tie will be first done on the small loops which are there, and we will see preparing pseudo sections with the help of strike line and deep lines. We'll try to see how the match is. If the match is not good, we go back once again and try it from the beginning. Once the match is good on the smaller loops, the bigger loop and the biggest loop, we impose all the two-way time on the short points and we try to contour them. Based on the contours, whether it is a high or a low, we understand which are the structural prospects which may be filled with hydrocarbon, and also we also understand the depot centers. The faults has to be understood whether they are sealing faults or leaking faults. The faults which are leaking faults helps for migration of hydrocarbon from the depot center into the structures. The structure should have cap, the cap should not breach, the fault should be then sealing, and the cap, if it is not breached, and the structure is formed after the hydrocarbon migration has happened, then it is a bald-headed structure. There is nothing inside it. Whereas, if the structure is formed and then the hydrocarbon went inside and then filled it, and there is no way to breach the cap, the structural integrity is there, those are the places we look for hydrocarbon. Those are the places where we see the locals, and that is structural interpretation. In separate lectures, I have told you that the easy oil are already explored. Structural highs and lows are the methods of the past. We are looking for lensoidal sand, we are looking for channels, we are looking for cut and fill structure. We are trying to see how this cut and fill, are they amalgamated or they are individual, how are they spaced, whether it is a low strand system track or whether it is a TST, where is the maximum flooding surface. These are some of the new tools which are utilized today to understand where the stratigraphic traps are, where the hydrocarbons are present which are difficult to find out by simple interpretation, and we have separate modules for the same which you have been taught of, and we hope that with the basic understanding and seeing couple of seismic section from the marine, from the shallow offshore, deep offshore, you will be able to understand the neritic diagram better. You will be also understanding the depositional environment and depositional sands to be interpreted for finding the hydrocarbon local. Thank you very much.